In this project, we will simulate the external airflow over a mountain. The study of natural phenomena has always been of interest to researchers. The purpose of this project is to study the airflow and its heat transfer on the surface of the mountain that it encounters in its passage, which is also effective in determining the air passage for the aircraft. In this project, the air enters the fluid domain with a velocity and temperature of 8 meters per second and 297.5 Kelvin respectively. The energy model is activated due to the nature of the flow, which is of the external flow type, and considering the airflow velocity, which has consequences such as flow separation and vortices behind the mountain, the K-epsilon Standard model has been used to analyze the turbulent flow. The geometry of this model is designed in ANSYS Design Modeler software and consists of an airflow inlet, the mountain itself, and 3 different pressure outlets, including top and side walls and the main outlet. The model of the present project is meshed in ANSYS meshing software, and the mesh type used for this geometry is unstructured, and the element number is equal to 1,250,044. Under the General Setup tab, you can see different buttons from scales to units. By clicking on a scale, a new window will appear showing you the domain extents of your geometry. Also, under the view length unit section, you can see the default geometry units, which is meter in this project. Also, under the scaling section, under the mesh was created in, you can change the settings in order to activate the scaling factors beneath that. For example, your geometry and mesh was designed in a software which its default unit was millimeters. By activating these scaling factors, you can change this factor to your desired factors in order to set the length to the appropriate unit. By clicking on check button, you will see that under the console tab, the Fluent software will start to check your mesh for any errors. Also, by clicking on report quality, again in the console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. By clicking on display button, a new window will appear which you can see different parts of your geometry. Now in the appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on display so that the software will show you that part. Now there are several assumptions taken into account for this project. First, the type of our solver is defined to be pressure based since we are dealing with incompressible flows. Also, the velocity formulation is taken to be in absolute form. And as for the time study, we have selected the transient time study since we are dealing with a time progressing phenomenon. As you can see, after double clicking on the energy button, in the appeared box, we have enabled the energy equation since we want to account for the temperature changes in our computational domain. After double-clicking on the viscose button, a new window will appear. In the appeared window, you will see that we have chosen 2 equations, standard K-epsilon, to solve for our fluid flow. The standard K-epsilon model is one of the most renowned models for solving the turbulent fluid flows, and actually 2 equation K-epsilon model allows the determination of both a turbulent length scale and time scale by solving 2 separate transport equations. Now, if you click on the inlet boundary, you can see that the type of this boundary is defined as velocity inlet. By clicking on Edit button, a new window will appear in which you can change the settings for this boundary. In the appeared window, under the Momentum tab, in front of the Velocity Magnitude section, you can see we have entered the value of 8 meters per second. Also, if you click on the Thermal tab, you can see the temperature of the airflow entering from this boundary. And if you click on this outlet boundary, you can see that the type of this boundary is defined as pressure outlet. If you click on Edit button in the appeared window, the most important point you should pay attention to is the gauge pressure, which is defined to have a value of 0 Pascal, meaning that our airflow will exit our computational domain to the atmosphere. And if you click on this outlet boundary, you can see that the type of this boundary is defined as pressure outlet. If you click on Edit button in the appeared window, the most important point you should pay attention to is the gauge pressure, which is defined to have a value of 0 Pascal, meaning that our airflow will exit our computational domain to the atmosphere. And if you click on this outlet boundary, you can see that the type of this boundary is defined as pressure outlet. If you click on Edit button in the appeared window, the most important point you should pay attention to is the gauge pressure, which is defined to have a value of 0 Pascal, meaning that our airflow will exit our computational domain to the atmosphere. Now if you select each of the wall boundaries and then click on Edit button, in the appeared window under the Momentum tab, you can see the stationary wall motion along with no slip shear condition are defined for these walls. Also, if you click on the Thermal tab for this wall, you can see that the heat flux thermal condition is defined and the value of heat flux is defined as 0 watt per meter squared, meaning that this wall is adiabatic. Now if you click on the Thermal tab for this wall, you can see the temperature thermal condition is defined and the value of temperature over this wall is defined to be equal to 300 Kelvin. After double-clicking on the method, you will see that a new window will appear showing you the pressure-velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first-order upwind and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. We may also change the under relaxation factors. These factors may be between 0 and 1. Based on the simulation and the project we are doing, we may change these under relaxation factors. But remember that the values set in here are the recommended values for the project, and we highly recommend you to not change these values. There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing the 0, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the New, you are able to choose between different reports. For example, you can define a mass flow rate report on an arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, it may be a sign that your simulation has reached convergence, but the residual must be checked as well. Now if you expand the report definition section and double click on the first report in the appeared window, you can see an area weighted average report has been defined over the field variable of velocity over the surface of outlet. After double-clicking on the residuals button, a new window will appear. In the appeared window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. After double-clicking on the initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the compute from drop-down list and clicking on one boundary. For example, by clicking on compute from all zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software.
We double click on Run Calculations button, and in the appeared window under the parameters we enter the values of number of time steps and time step size and max iteration per time step, as you can see in this slide. After that, we click on Calculate button and the software will start the simulation process.
Now in this part we have extracted 3D and 2D contours by the means of CFD Post software.
In order to extract a 2D contour, we first have to define a plane. To do that, we click on Locations and then go over Plane and click on it. On the low left side of the software window in front of the method, we select ZX plane and we leave the value of Z unchanged so that this plane will be created in the middle section of our geometry. Now that we have created our needed plane, we click on Contours button and accept the appeared window in order to extract a 2D contour. Again, on the low left side of the software window in front of the locations, we select our defined plane, and in front of the variable we select our desired variable, which in this slide we are going to select the velocity. After that, by clicking on Apply button, the software will show us this contour. In this slide, you can see the velocity distribution over a plane which is placed on the middle section of our computational domain. Also, you can see that behind the mountain there is a region with a decreased velocity indicating that vortices are being generated in that region. You can simply create and extract another contour by just changing the variable section, for example from velocity to temperature, and then by clicking on Apply button. And in this slide you can see the temperature distribution over the same plane, and you can easily see that the temperature has increased near the mountain surface. And finally, for example, in order to extract the pressure distribution over the surface of the mountain, you can just simply change the locations from plane number 1 to the mountain wall surface, and then by changing the variable section to the pressure, and then by just clicking on the Apply button. And finally, in this slide, you can see the pressure distribution over the surface of the mountain.
Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.